Hey, welcome everyone. Good to be doing this again. Do you know how to model a gas turbine? If not, that's okay. Let me tell you a quick story. Just a few months ago, I was working on a decarbonisation project, and the client wanted to study the impacts of running their existing turbines with hydrogen-rich gas. So basically, they wanted to continue running their operations, but they wanted to increase the hydrogen content of their natural gas to up to 20%. Obviously, they had some concerns as to how is that going to affect the performance of the turbine. They also wanted to understand how is that going to affect the downstream applications, because the gas that comes out from the turbine, they were using it for steam generation and also for process heating. And we're also curious about how is their whole project going to reduce their carbon footprint. So as part of the process design, my role was to develop this base model, so to speak, basically just replicate what they have there on site, and then start to introduce hydrogen into the gas and see what the implications were. I did that and everything ran smoothly, and I just thought, you know what, how about I share this knowledge with the community, and hopefully you might learn something, and I might learn something from your comments. Now go grab your popcorn, coffee, or whatever that you like to nibble on when you work, and then we'll get right into it. I'll see you on the other side. Okay, let's start with adding the components. And if you know how to do this, you might as well just skip this bit. But if you're keen to know how to add components, stick around. So the components for our gas turbine will be methane, ethane, propane, butane, all the way to N-hexane, a fair bit of carbon dioxide, nitrogen, and in this instance, I'm going to leave out the hydrogen. That will come at a later stage when we do the fuel gas manipulation. So for now, I'll just insert these components, and that is methane, ethane, propane, and N-butane. So what I just did there, just press shift and then select these three, and they should go into that side. And then I've got N-butane, add, and hexane, add. Then carbon dioxide, I'm going to search for carbon dioxide, CO2, add, and nitrogen, there's nitrogen, add, and lastly, we're going to add also oxygen, because that's what we're going to use for the combustion. Then the other component that wasn't in the spreadsheet there earlier is H2O, because water is one of the byproducts of combustion. So it does form one of the components, H2O. That's water. Then that's it. We've got all our components. Then the next thing is to insert the fluid package. Just click there on fluid package, click add, and then we're going to use Peng the famous Peng for the hydrocarbon system. If you do need to understand how we choose these property packages, I've got a separate video where I take you through all these methods of how to choose the property package. So we've got our property package all selected. Now, while we're here, I think the next best thing is to also set up the reaction set, because we're going to need this reaction set for the combustion side of the turbine. The combustion chamber has got some sort of combustion reactions happening in there. So we're going to set up the reactions. What you do, just click on reaction, and then it will put a folder here that it will call set 1. What I normally do, I'll just rename this to combustion reaction. Here we are going to use a conversion reactor, because it converts almost all the hydrocarbons in the feed to produce the CO2 and water. So a conversion reactor would be the simplest reaction we can use. However, it does come with a fair bit of upfront work. So I'll show you what I mean by that. So we've got our reaction 1. I will call this one here methane, because this will be the combustion reaction for methane. And then once I've renamed it, I double click on it again and another window should pop up. And to put in the reaction components, you're going to start with methane. It reacts with oxygen and it produces CO2 and water. The next thing that you would need to insert is coefficients of the balanced reaction. I've got that sort of done already in the spreadsheet here. I will show you how it looks like. So this is the reaction that we just put in there. Methane reacting with oxygen produces CO2 and water. So the coefficients that I was talking about earlier, these are the ones that are in here. For methane, going to be -1. And then for oxygen, going to be -2. And then for CO2, it's going to be a +1. And then for water, it's going to be 2. The reason why we've got that is, you see, for the reactants, those coefficients are going to be negative because of we're consuming the reactants, and then the products are going to be positive because we are producing them. That's the logic. While we're here, I will just take a screenshot of this because this process will take about, I don't know, 7 minutes to complete to set up all these 5 reactions. If you know how to do this, you can skip this step and then go to the next one. I will slowly but surely run through the process. We said that was -1 for methane and -2 for oxygen, a +1 for carbon dioxide, and +2 for water. So you'll see if your stoichiometric coefficients are correct using the balanced chemical reaction, the balance error here should be 0. And then once that is 0, you come to the right-hand side. The base component is methane because that's what we're trying to combust in this reaction. And we're going to look at the overall reaction. You can go with vapor phase because this reaction is in this simulation, everything is in vapor phase. But just to be safe, just go with overall. And then the component, which is methane, we are converting 100% of it. So we're saying after this reaction happens, we've converted all the methane. There's nothing coming out in the flue gas. Then we're going to repeat this process for all the other 4 remaining reactions. So this one is set. You should see a green tick to show that it is fully configured. Now we're going to insert the next one. Just click on add reaction and then add the conversion reaction. And I'm going to rename this to ethane. I double click on it and then it just opened the window. That's fine. We can just go ahead and insert the components. Ethane reacts with oxygen, produces CO2 and water. And the stoichiometric coefficients, you go back to that balanced chemical reaction. I'm going to put this spreadsheet again here. This is -1, -3.5, +2, and +3. But don't you worry too much. I'll put a link to all these documents in the description. -1 for ethane and -3.5 and +2 and +3. Then the balance error is 0. We know we are good and we are converting 100% of the ethane. Press enter and it should turn green. That's good. So the ethane reaction is now fully configured. We're going to add another one. Add reaction. Okay, I'm going to press enter. Conversion reaction, and that reaction we're going to call this one propane. And double click after you've renamed it to bring up the input window. Propane reacts with oxygen and produces carbon dioxide and water. There's the coefficients. There's -1, -5, +3, and +4. And enter. Yep, balance error 0. We're good. We're converting 100% of the propane. Yep, it's green. And now we're going to insert the next one, the conversion reaction. This one is butane. And double click to bring up the input window. I've got butane reacts with oxygen, produces CO2 and water. Coefficient is -1, -6.5, +4, and +5. Enter, and we are converting 100% of the butane. That's good. And the last one is hexane. And then double click to bring out the input window. We got N-hexane reacting with oxygen, produce CO2, and produces water. And the stoichiometric coefficient is -1, -9.5, +6, and +7. And we are converting 100% of that hexane. And we are good. Now you'll see it still has some sort of a warning. It says not attached to the fluid package. So to attach this to our fluid package, you just click on here, add to fluid package. That's the fluid package we selected earlier, the Peng Robinson. And once we've done that, we have pretty much done the upfront work. Now we're going to start with the fun part of it. Then you go to the simulation environment. I don't know why HYSYS always does this. It always has this tool palette hanging. I'll dock it here on the left-hand side and minimize this so we can get space. That looks better. Now, the first thing that you need to do is to insert the material streams. I'll start with the air. Just click on the blue stream there and then double click on it. Bring up that window, rename it to intake. And the temperature, it's 15 degrees based on the datasheet. One thing I forgot to mention is I like to use kPa gauge instead of kPa absolute. So I'll change my unit set to this one that I've done earlier. Again, if you want to know how to do these custom units, let me know in the comments if you'd like me to make another video to show you how to set up specific unit sets for a specific project. The air pressure, it is atmospheric pressure at sea level. So that will be 0 kPa gauge. And we need to also include the mass flow rates. How do you know what the mass flow rate is for your turbine? It is included in the turbine datasheet. Let me bring it up here. So if you look at the Titan 250 datasheet, it will have the air flow rate. This is the datasheet for the Titan 250, and that's the inlet airflow, 73.2 kilograms per second. These are the minimum information that the manufacturer will be giving you, 73.2 kilograms per second. I'll show you one thing that I need you to be very careful of when you do this. Punch in 73.2, but you see what HYSYS is doing? It's giving you that in kilograms per hour. You need to change this to kilograms per second. Just make sure you don't miss this step because of this. That 73.2 kilograms will be converted to kilograms per hour, and that's your flow rate in kilograms per hour. Now, the last thing that we need to do is to put in the composition of this air intake. Air is predominantly made up of oxygen and nitrogen. So it is typically 21% oxygen and 79% nitrogen. This is oversimplifying it. There's also argon and other noble gases in there. But for now, we'll just stick with your typical air composition of 21% oxygen and 79% nitrogen. Then that intake stream is fully specified. The second step is to insert your fuel gas, right? This is going to be a little bit interesting. I'll show you what you need to be careful of in this one here. We're going to rename that to fuel gas. Fuel gas, call this battery limit fuel gas. So this fuel gas is still coming from the supplier. It's just coming in at our battery limit. And the inlet temperature will be 15. And for our specific project, this gas was coming in at 800 kPa. It could be coming at any number. You just need to make sure that you use the battery limit conditions of your fuel gas feed. And there's a reason for that. I will show you just now. Here is the thing that I wanted you to be aware of. At this stage, we don't know what the actual fuel gas flow is. We're trying to figure that out. And we're going to use HYSYS to come up with that number for us using the information that we are given in the datasheet. And this is how I did it. I'll just put in here an arbitrary flow rate. And the reason I do that is just that I want to calculate the lower heating value of the gas based on the composition. And once I know the lower heating value, then I can back calculate the flow rate. Then you just come here to the composition. I'm going to open that spreadsheet again. Fuel gas composition. And let me just try to split screen here and see if that will work. And I'll just try and copy what I've got here because I've got all these in the same sequence up until the nitrogen. I'll copy this. And then if I just press enter here, it will open another window. I don't know why HYSYS does that all the time, but it's okay. Then it pastes all those components. The oxygen in the fuel gas is 0. We don't have any water in fuel gas as well. And press OK. Boom. And then that stream is fully specified. Okay. Now we've got our battery limit fuel gas all sorted. Now we need to go back and work out the actual flow rate of that fuel gas. And how do we do that? If we go back to the data sheet, you'll see that in the second page here, the heat rate of this turbine is 9,150. And at this heat rate, it produces 23,100 kilowatt of electricity. What is heat rate? Heat rate is nothing too complex. It just specifies how much fuel energy is required to produce 1 kilowatt of electricity. And the reason why the manufacturer does that, they don't know your gas composition and they don't know what your lower heating value of the gas will be. So they just say, for you to be able to produce 1 kilowatt, this is how much energy you're going to need from your gas, right? And then now that we know our lower heating value, then we can back calculate the flow rate. And that's what I'm going to show you how I did it here in the spreadsheet. It's a relatively simple calculation, but sometimes you might get a little bit confused. So I've stated what the datasheet tells us there. It's the power rating of the turbine, and then I've got the heat rate and the lower heating value. So multiply this by that to get 211,365,000 kilojoules per hour. And then I divided that by 1,000. Then you divide this by the lower heating value, and then you get the cubic meters per hour gas flow rate. You can double check my calculation. Then this is what we're going to use in HYSYS as our fuel gas flow rate. So I'm going to remove that 1 cubic meter per hour that I just put in there and insert this 6,211. And then that sort of sets the scene for the simulation to start. We've got air, we've got the battery limit fuel gas. Now let's think about what happens after. We've got ambient air. We know it goes into the turbine, and then before it goes anywhere, it goes through a compressor, right? Inside the turbine. So we're going to model the compressor here. That's our air intake compressor. I'm going to label it air comp. The inlet stream is the air intake, and the outlet, I'm going to call it compressed air. Compressed air. And the energy stream for the compressor, or this is the power that the compressor consumes. I'll call it Q air comp. And then you ask, so, yep, what do we do after that? So how do we know the compressor duty? We don't really know the compressor duty, but the data sheet tells us that this compressor has a compression ratio of 24:1. See that? The pressure ratio is 24:1. So in HYSYS, we just come to the parameters within the compressor unit operation, the parameters, and then you specify the compression ratio of 24. See that? Pressure ratio 24. One other thing that you might need to take into consideration is HYSYS will have a default adiabatic efficiency of 75. Most modern turbines, they've got a higher efficiency, somewhere between 85 and 90. So for us to be conservative, I will just go with 85% efficiency. And once you do that, just press enter, and the whole air compressor is fully specified. So we can see that we are consuming about 37 megawatts of power to compress that amount of air coming in. Where is that power coming from? It's coming from the turbine. It's coming off from the expander. So in a way, we will have to come up with a way to link the turbine power output to this compressor, because the turbine is actually what drives this compressor. Yeah. And that's good. Then we can also look at the battery limit fuel gas. And the battery limit fuel gas, okay, I forgot to mention, the discharge pressure is 2,330 kPa. So it is logical to say then this battery limit fuel gas will need to be compressed as well to be able to match the compressed air pressure, so they can both go into the combustion chamber. Otherwise, this 800 kPa is not going to be enough to feed into the turbine. And in our project, yes, we had a fuel gas compressor. Again, depending on your battery limit conditions, you might not need the fuel gas compressor. Your gas might be already at a higher pressure. Then you don't need the additional step of a fuel gas compressor. Compressor is going to be pretty much the same steps as the previous one. The inlet is going to be the battery limit fuel gas, and the outlet, I'm going to call it compressed fuel gas. And then in terms of the duty, we know the duty of this compressor because we had a data sheet, but we know that we want the discharge pressure to be the same as the compressed air. So we will specify the discharge pressure. You double click on the discharge stream, and then you specify the discharge pressure to be 2,330. And once you've done that, you've got the compressed air and the compressed fuel gas matching the same pressure. Then the two streams are good to go into the combustion chamber of the turbine. So as you can see, we are slowly but surely building the turbine here, right? Let me do this. Now we are going to use a conversion reactor. If you don't know how to spot it here from this list, you can search for it here. I'll just say conversion reactor. There it is. That's the conversion reactor. I just double click on it and it comes to the simulation environment. I'm going to double click on the icon and just bring this to the middle so I can work on it. I'll call this the combustion chamber. So I guess you've already noticed by now that the first thing that I do is to rename my unit operations as I put them into the simulation environment. That makes life way easier when you start working with the model after 6 weeks or 6 months. When you come back to it, you know what each unit operation or stream actually means. Then the inlet streams, you've got 2 inlet streams coming in there. You've got the air, and you also have the compressed air, which is this one here. And you've got the compressed fuel gas, which is that one there. They're both going into the combustion chamber. And in the combustion chamber, we're going to have hot flue gas. So basically, this is where the reactions are going to happen. And what comes out is the hot, I'll call it high pressure, high temperature flue gas. But there's one other thing that you'll see, because that air intake is actually combustion air at the stoichiometric level, and we are using excess air. Most turbines actually use close to 100% excess air. You'll see those in the next set of videos that will follow on how we assess the whole turbine performance, including CO2 reduction, percentage excess air used for the combustions, basically the optimization part of this process. At this stage, we're just setting up the base model that will match the manufacturer's datasheet. And then HYSYS will also need a liquid outlet stream. We don't have any liquid in this simulation, but I'll just call it condensate, so we can get it to do the calculations as it should. You'll see here, it says it requires a reaction set. Remember earlier when we were putting all the components, we did the work up front. We've put in the reaction set. So we are now in a relatively easier position to just insert the reaction sets. So to do that, you just come to the reactions, and in this drop down menu here, you go the combustion reactions. So you'll see it will have all 5 of them: methane, ethane, propane, butane. And once you do that, it will turn green to say your reaction has actually converged. So we've modeled the air compressor, fuel gas compressor. Oh, I made a mistake here. I didn't rename it. I need to rename this to fuel gas compressor. And then now we've got this far, we need to use up all this energy. This is the driving fluid that actually does most of the work. It is going to be expanded in the turbine, and the turbine will start to generate electricity. So we're going to look for an expander. The turbine is modeled as an expander, right? There's our expander there. I'll double click on it, and then I'll call it T turbine expander. And what's going in is the high pressure, high temperature flue gas. What goes out is the hot, I'll call this hot flue gas. The reason I just call it hot flue gas is now it has dissipated most, if not all, of that high pressure. So it expands and cools at the same time to liberate all that energy in the gas to drive this turbine. Q of the turbine, I'll call it Q turbine. So this is the power that the turbine produces. You'll see even the arrow, it's coming out of the turbine. This is a HYSYS sort of showing you that the expander actually produces power rather than consume it. You'll see this one here with the air compressor, it is consuming power. The power is going into the compressor. I hope that makes sense. You'll see it is asking for the duty for the expander. We don't know the duty, but we are told that the gas is coming out at 460 degrees Celsius. So we're going to use that information from the turbine data sheet. You see there, exhaust temperature is 460. So in here, we're going to specify 460. But before we do that, we need to just address efficiency of the expander. Similar to the compressor, HYSYS will give you a default of 75%. These turbines, again, the expander would have entropic efficiency upwards of 85 all the way to 95%. And again, to be conservative, we just use 85%. We might need to come back to that number just to see whether it aligns with the data sheet. And then there's two ways to do it. You can come to the hot flue gas and then just specify the outlet temperature there. That's the only variable that you need to specify, and it will do the calculation. Or you can double click here, or you can do it from the worksheet in the turbine itself. You can come back here and it will have all the inlet stream and the outlet stream, and then you can specify that 460 outlet temperature here. Then press enter and it should turn green. And there we are. So it has converged. And this is very exciting. We've done most of the modeling. Now we just need to do some back calculation using the spreadsheets. I hope this makes sense so far. Now we're going to work out how much power this turbine is producing. It's producing almost 60 megawatts, but we know not all this power is used to generate electricity. Some of it is used to run the compressor. And to find out how much is actually left to generate electricity, we can use the spreadsheet, or at least that's what I did. I used a spreadsheet. And the nice thing with the spreadsheet is once we start doing the sensitivity analysis, we can be able to get the immediate results using this sheet. Just double click on it and then rename this to the turbine. I'll call it turbine energy balance. And then once you've done that, you come to this tab here, spreadsheet. In this spreadsheet here, what I normally would do, I'll bring in the key parameters that I'm interested in. And the first one would be the fuel gas. I'll use the A column and the B columns. So in the A column, we just put in the description, which is the fuel gas flow. And I will use the B column to put in the actual fuel gas flow. So the fuel gas flow, remember we got it from here, right? And to bring that into that cell there, there's many ways to do it, but I find this way to be the quickest and the most safest way to do it. So I know the fuel gas flow is 6,211, right? So I'll just click on here, drag, and drop it in here. Boom, and that's it. You don't have to do anything fancy, just that drag and drop. The next one would be the fuel gas lower heating value. To get the lower heating value of the gas, that will be in the properties list here. And you'll see the default list of correlations here is lower heating value, but this lower heating value is in molar basis. That it doesn't really help us that much. I prefer to work with lower heating value in volume basis, because everything that we do here is volume based. And you can see from this list, they don't have it there as a default list or default correlation. To edit, you just press the green plus button, and then you come to gas, and then you look for lower heating value in volume basis, right? And then you say apply. And now it should come down here on the correlation list. There is our lower heating value gas basis. And then I'm just going to do the same thing there. I could just take it and drop it there, but I want to show you the other way to do it, which is a bit of a long way to do it. But you can right click here, right click in the B2 cell, and then import variable. And then we know the variable was coming from the fuel battery limit fuel gas. Just double click there, and then we are looking for the volumetric flow rate. I'll say flow, and you go to the standard gas flow, right? And then add it to the list. Then you rename it to gas flow or fuel gas flow. No, this is what we're looking for here. Oh, the lower heating value. My bad, we're not looking for flow, we're looking for lower heating value. Let me take that back. It's LHV, lower heating value. You search for the lower heating value to bring out the calculator, and then you bring out the list. and then we're looking for the lower heating value in volume basis, and then we go for the overall. And then you rename it there and say done. So there it is there. That's our lower heating value. You can see that took quite a bit of time to bring it in. It also brought in that the standard heating, the standard flow rate. I'm just going to delete that. I don't need this. Disconnect. And I'm going to disconnect this. This was just me trying to show you how you can bring in the variables in a different way rather than a drag and drop. But drag and drop, for me, works out to be very quick and accurate. Now, the other thing that I normally do, which is not really a requirement, but useful if you interact with the people on site, because with a machine like this, the gas consumption will be expressed in terajoules per day or TJs per day. So HYSYS doesn't have the TJ per day sort of units. So you might want to manually calculate that. And I'll show you how you can do it. I'll label this as energy flow or fuel gas energy flow. Gas energy flow. And then I'll put the units here because of you won't find them in the HYSYS list of units. Then to do that calculation, I'm assuming you how to do your manipulation of units, but it will be just like just your standard Excel. Let me refresh. With HYSYS, when you do the calculation inside the workbook, you have to explicitly name the cells. For example, with this one here, we're going to multiply B1 and B2. So explicitly B1 times B2, and to make it days is 24 hours, and then we're going to divide that by a million to make it terajoules. So that should be around 5.07 terajoules per day. If you ask the people on site who runs this machine, they'll tell you, yeah, we consume about 5 terajoules per day. That's the language that they use, so it does help for you to compare what they tell you once you've done the base model. And then the other variable, the raw power produced by the turbine. So to do that, you just double click on the turbine and then you go to performance, and then you can see the power produced by the turbine is that 59 megawatts. Just click on there and then drag and drop it there, right? And then I'll call this turbine raw power output. And then we need to also do the same for the air compressor power consumption. So I'll just double click on here, bring this window down, and then you go back to the performance, and you'll see here it will say power consumed. So it does show you that the compressor is consuming about 36 megawatt of that power, right? And then I'll call this air compressor power consumed. And then the turbine produced about 59 megawatts and the compressor used up 36 megawatts of that, right? So the difference is used to produce electricity. So we can always come back here and say, okay, the electrical power generated is the difference of the raw power by the turbine, which is cell B4 minus B5, which is the air compressor power consumed. Then we are left with about 22.8 megawatts of electricity. Let me just change that to megawatts. I'll just say electrical power. I'll call this electrical power in megawatts. And then to do that, what I will do is I will just take this B6 divided by 1,000 to make it into megawatts. However, if I just do it like that, it's going to the units of a kilowatt in there. But we know that's not correct. It needs to be megawatts. So what you can do, you just come here. HYSYS will say the variable type is power. Yes, it is power, but the units are incorrect. So I'm just going to have it unitless, because I've got already my units in the description there. It says 22.86 megawatts. Now, the last thing that you might want to do is calculate the efficiency, just to check the efficiency of the turbine. The thermal efficiency is the energy input over the energy that is produced. So for our case here, to calculate the thermal efficiency of the turbine, it's going to be the flow rate multiplied by the lower heating value, and manipulate the units to be in megawatts, and then we divide that by the power produced, which is B1, multiplied by the lower heating value, which is B2, and we're going to divide that by 3,600 to make the units in seconds. That is the input power from the gas. So we want to divide B7 by the input power, which the B is the output power divided by the input power, times 100. Then we're going to click on here, change this to efficiency to percent. So you can just type P% and then there is it, you'll find it. So 38.93% efficiency of the turbine. Now we can do a quick check whether we are on the right path or we have completely missed the plot. So with this spreadsheet here that we've done, let's double check our simulation output to the manufacturer's datasheet. The datasheet says for all these conditions that we have modeled, their efficiency is 38.6, and we are getting 38.93. That's pretty close. And they are producing 23,000 or 23.1 megawatts, and we are producing 22.6 or close to 23 megawatts. As a base model, once you've done this, you've pretty much modeled the turbine. The other fun bit is now doing a heat recovery system on this hot flue gas. That will follow in the next video, because this one here, I think there's a whole lot to unpack. But I hope you have learned one or two things out of this. The last thing that I think we might want to do, just to wrap up quickly, is to just have this flow sheet look a little bit professional. And normally I would put in the stream tables onto the flow sheet. The most important one is this one here. So just right click on the spreadsheet icon and you go show table. This table will come up empty, and then just double click on it. And then we're going to put in all those variables that we generated from the spreadsheet earlier. It's from B1 all the way to B8. Then add. Then you can also put different descriptions for these. This one here was fuel gas flow. And then B2 was lower heating value. Oh, she's fuel gas, lower heating value. B3 was the energy flow. Energy flow in terajoules per day. And B4 was the turbine raw power. And we're not done. So we just double click on this again, and then we can rename it from here. This is the air compressor power consumed. And then B6 was the electrical power produced in kilowatts. And then this is the electrical power produced in megawatts.
And then B8 is the turbine thermal efficiency. Turbine thermal efficiency. There you go. So you've got this as a quick reference to check your model as you change stuff on it. And then you can do the same for the other streams. Just for, as an example, I just put one here just to show you how to do it. You just right click here on the stream and then show table. And I'd just like to put it there at the top. This is also another important thing that I almost forgot to touch on. So you see how the outlet pressure is coming out at a negative value. In real life, this is not correct. Yeah, you can't have the exhaust gas at vacuum. So that tells me the isentropic efficiency that we assumed earlier was actually a little bit low. So we need to increase it up until we get some sort of a positive pressure. In practice, that pressure could be anything between 5 kPa to 10 kPa. This is one tweak that you have to be careful of and check. So I'm going to come back to the turbine and then go to the parameters. And I'm going to change this to, say, 80, 88, 86. And that's minus 12, 88%, minus 1, 90% thermal efficiency. We can go all the way to 95. So you see, once I go to 90%, the pressure is about 10 kPa. It's a little bit high for a gas turbine, but it shows that the isentropic efficiency of the expander is in the high 80s, close to 90. And then here, the variables that I'm interested in is not really molar flow, it's the temperature, the pressure, and the mass flow rate. I'll add the mass flow rate. And then I'll take off the molar flow rate. And you can do the same for all the other streams. Look, I hope you have enjoyed this video so far. There's still a lot to unpack. We are not completely finished, but we've got the base model matching the datasheet. So from here, we need to model the heat recovery side of the process, which is another exciting video that we will be doing in the next few weeks or so. Okay, that's a wrap for that video. And thank you for sticking around. I understand it was a bit long, but we had to go through all those steps just to make sure that the base model actually works and is correct. If there's anything that I might have left out or you felt like I didn't explain too well, just feel free to leave me a comment and I'll address it. I will also be leaving a link where you can download all the documents that we've been using, the datasheet, the spreadsheet, and the HYSYS model for you to play around with. I am not quite sure when I will be releasing the next follow-up video. However, it's definitely coming. And until then, stay safe, enjoy the popcorn, enjoy the coffee, and I'll see you on the other side. Cheers for now.